I will continue to talk about elliptic curve with complex multiplication over real number field. I will talk about lemma 3.1 here. Let O be an order in a quadratic field K. Let lambda be a fractional or ideal. Then the following are equivalent. First, lambda is a projective O module. So it means that a fractional O ideal can be viewed as a O module if lambda is a proper O ideal. So when lambda is a proper O ideal, then lambda is a projective O module. And for every prime P, lambda tensor with the ZP is a principal fractional O tensor with ZP ideal. Okay, from now on we assume that K is an imaginary quadratic field. If O prime is contained in O, are quadratic order in K, their discriminants are related as follows. Discriminant of O prime is the index of O prime squared times discriminant of O. Discriminant of O prime is the index of O prime under O squared times discriminant of O. For an order O in K, we define the conductor F is equal to the index of O under OK. Let us write delta K for the delta of OK. Thus, if O has a conductor F, we have delta of O is equal to F squared delta K. Observe that delta of O is negative and congruent to 0 or 1 modulo 4. We call integers imaginary quadratic discriminant. For any K and for every F belongs to Z plus, that is integer bigger than 0. Z bracket F squared delta K times F for any K and F belongs to Z plus, Z bracket F squared delta K plus F times this square root of delta K divided by 2 bracket is the unique order O in K of conductor F. It follows that for every imaginary quadratic discriminant delta, there is a unique imaginary quadratic order O of delta of discriminant delta. Section 3.2 Basics on CM elliptic curves. Let A over F be an abelian variety over a field F. Endomorphism of A, we means the ring of endomorphism of A endowed with the structure of GF module, where GF means the Gauss group of F bar over F. It is known that the endomorphism 0 of A is equal to endomorphism of A. Tensor product with Q is a semi-simple Q algebra, and the endomorphism of A is an order in endomorphism 0 of A. That is the endomorphism algebra. What is the relationship between the endomorphism algebra and the endomorphism ring? Endomorphism ring is an order in endomorphism algebra. When F has characteristic 0 and A is equal to E, is an elliptic curve. Endomorphism 0 of E is either Q or an imaginary quadratic field. So the endomorphism algebra can be viewed as an imaginary quadratic field. In the later case, we say that E has complex multiplication, Cm. Thus, endomorphism ring of E is an imaginary quadratic order inside the imaginary quadratic algebra. And endomorphism ring is an order of imaginary quadratic order O. And we say that E has OCM. We summarize some facts of CM theory. Proof are Proofs are found throughout the literature. Facts 1. A. There exists at least one complex and elliptic curve with OCM. So that is for every O. For every O, there is at least one complex elliptic curve with OCM. Let E and E prime be any two complex O of delta CM elliptic curve. The J invariant of J of E and J of E prime are Galois conjugate algebraic integer. In other words, J of E is a root of a monic polynomial with Z coefficient, and it is a Hilbert polynomial. And J of E prime is also the root of such polynomial. Thus, there is a unique irreducible monic polynomial that we call the Hilbert polynomial of discriminant delta belongs to the Z bracket T, whose roots are the J invariant of O of delta CM complex elliptic curves. The degree of H delta of T is the class number H of delta is equal to the Picard group of O of discriminant delta and the number of the Picard group. The order of Picard group is the class number. In particular, when O is equal to OK, we have a degree of the Hilbert polynomial of discriminant delta of T is equal to the class number of K. Let F discriminant is equal to Q bracket T bracket divide quotient by H delta of T. Then F delta can be embedded in a real number, so in particular is linearly disjoint from the imaginary quadratic field K. Let K delta denote the composite term of F delta and K, the ring class field of the order O. Then K delta over K is abelian with Galois group canonically isomorphic to the Picard group of O. Let E over C be an elliptic curve with OCN. By the uniformization theorem, there is a lattice lambda belongs to C, such that 1 belongs to lambda, and E is the isomorphic to C over lambda. Then lambda is a fractional OID of K, and the O of lambda is equal to O, so lambda is a proper OID. So by lemma 3.1, lambda is a projective O module. So lambda is an O module and it is proper OID. Conversely, if lambda is a rank 1 projective O module, then E lambda, that is E parameterized by lambda, is equal to lambda tensor product with C quotient by lambda. So lambda quotient by lambda can be viewed as E lambda is an elliptic curve because lambda tensor product with C over lambda under the basis of the order O is elliptic curve E of lambda. Then the C isomorphic class of E lambda depends only on the isomorphism class of lambda as an O module. So lambda can be viewed as an O module. The map from the lambda to E of lambda induces a projection from Picard group of O to the set of isomorphism classes of elliptic curve of E over C with the endomorphism ring of E isomorphic to O. Thank you very much.